Hello everyone and welcome back to another episode on complete reference to CUDA programming. In previous episode, we have seen how we can divide the task among multiple threads in case of vector addition program. We tried to parallelize that vector addition program using a single block, and we realized that here the problem is we have maximum limit on number of threads per block, that is 1024. So in that case, the question is, what if your input size n is greater than 1024? So what if I'm having the number of elements in an array which is greater than 1024? So in previous solution, we have seen I can launch only one block, and in case of one block, I can launch multiple threads. But the limitation on multiple threads is 1024. So if I'm having n greater than 1024, so I'll not be having sufficient number of threads to perform that task. To overcome this problem, there are two ways. Either we can use concept of stride, or we can consider launching multiple thread blocks. So out of which, let's try to understand what is this striding concept. So just to demonstrate on this slide, I'm not going to consider the maximum number of threads per block limit as 1024. So we will consider it is only 4, so that we can visualize how the computations can be performed. So here I'm assuming the maximum number of threads per block equal to 4. That is the maximum I can launch. And initially I'll ask all these threads to perform their corresponding indexed addition. So thread 0 will perform addition of a of 0 plus b of 0 to get c of 0. And similarly, remaining threads will perform that computation. Now question is, we are having 8 elements in my array, and we are having only 4 threads. So who will perform the addition of corresponding remaining elements here? And what I can suggest here is, same threads, after completion of their corresponding this job, they will move towards the next element of the arrays. And how we can ensure that? By concept of this stride. So stride is nothing but just jump size. So once thread perform its allocated task, it is going to jump to the next element, but that jump size is nothing but the stride size here. So in first iteration, all threads will perform this addition, and in next iteration they will move towards the next 4 elements like this. So thread 0 is now performing addition on 4th element, then thread 1 is performing on 5th, thread 2 is performing on 6th, and thread 3 is performing addition on the 7th element. But question is, how to determine that jump size? It is simply nothing but the size of your block, because first 4 threads are performing the addition on first 4 element. Now we are remaining task with next 4 element. So that's the reason we are having the jump size or stride equal to 4. Right? So this is how we can assign same number of threads to perform additional task now. Okay, and let's see how we can modify our code now. So again, the coding part is going to be almost same. So tid equal to thread id x.x, which is going to retrieve id of each thread. And now here I'm having I equal to tid. So there is a typo here. In this particular case, I is supposed to equal to tid, not 0. And I is less than n to ensure that we are not going past that n value. And we are going to increase I value by blockdim.x. Why blockdim.x? In previous case we observed we are having 4 threads, so we have to increase the value by 4 to find out next element on which the thread is supposed to perform the operation. So here I equal to tid, I less than n, and I plus blockdim.x. So let's see what thread 0 is going to perform. So thread 0, it will get tid equal to 0. So I will be initialized to tid, that is 0. That means initially thread 0 will perform addition on c of 0 equal to a of 0 plus b of 0. Next time the I value gets incremented by blockdim.x, and in our previous case the dimension of block was 4 here, so every time I gets incremented by 4. Now I value becomes 4, so same thread number 0 is going to perform addition on c of 4 equal to a of 4 plus b of 4, right? And similarly it will go on increment the I value by blockdim.x, but condition here is I must be less than n, that is it should not cross the total number of elements or size of your array. So similarly, if I focus on thread 1 now, so it will get TID equal to 1 because the ID of the thread 1 will be 1, and it will start computing from I equal to 1. So it will initialize I equal to 1. So it will perform C of 1 equal to A of 1 plus B of 1. Right? So we can see it is indexed, working on the index 1. Then it will increment the index by 4. It will become 5, then 9, and then 13, and so on. So same way thread 2 will perform, and let's get final, we are having thread 3, so it will get TID equal to 3, I equal to 3, it will start, so C of 3 equal to A of 3 plus B of 3, and then next time increment by 4, so it becomes C of 7 equal to A of 7 plus B of 7, and so on. Right, so you can see here I had limitation on number of threads per block, and that's why I assign the extra task to the whatever threads I'm having with me. But there is another problem with this implementation because we are launching very limited number of threads. As I mentioned earlier, on GPU we can have thousands of cores. In recent GPU I'm having, let's suppose, 6,000 cores, but out of which I'm launching only, the limitation is 1024 threads per block, and I'm launching only one block. So all these 1024 threads get scheduled on 1024 cores. And if I'm utilizing only 1024 cores out of 6,000, our complete resource utilization will be very poor. If I'm having 6,000 cores, out of which I'm using only 1,000. So there is no point in doing this sort of thread organization and work distribution, because I want my GPU to be utilized at the fullest. So this is the limitation if I'm launching only one thread block, and even though I manage to perform the entire operation on the vectors of size greater than number of threads, still we are with the problem of poor resource utilization on GPU. And that problem we can resolve using by launching multiple thread blocks in a same kernel. So in the next episodes, we will explore how I can launch multiple thread blocks. But before that, let's see the implementation of these two strategies.